Imagine trying to squeeze the entire 13.8 billion-year history of the cosmos into a box sitting right there on your desk. Welcome to this explainer, where we're going to dive into how scientists are attempting to do exactly that. It's a topic that just completely bends the limits of human comprehension, blending cutting-edge computation, theoretical physics, and, honestly, a massive dose of sheer human ingenuity.
We're unpacking the absolutely mind-bending reality of cosmological simulations, largely based on the captivating work of astrophysicist Dr. Andrew Pontzen. We'll explore how recreating the stars digitally helps us figure out what's really lurking out there in the dark, where it all came from, and how the vast, silent mechanics of deep space actually relate to our lives right here on Earth.
So have you ever tried to fit a 13.8 billion-year-old universe inside a computer? It sounds completely impossible, right? But to understand our origins, cosmologists basically have to do exactly that. They have to shrink the infinite down into something a processor can actually handle. I mean, to put the sheer scale into perspective, Earth is nearly 13,000 kilometers across. You could fit our entire planet into the sun over 1 million times. And the sun, it's just one perfectly average star out of hundreds of billions in the Milky Way alone. Trying to compute the sheer scale of billions of galaxies, well, it isn't just hard, it literally borders on the absurd.
Now, what's super interesting is that Dr. Pontzen's journey to coding the cosmos didn't start with some multi-million-dollar telescope perched on a mountain. It actually started at age 7, down in a damp basement, hunched over a plasticky ZX Spectrum computer with one of those terrible squishy rubber keyboards. Loading a rudimentary game like SatOr back then meant fast-forwarding physical audio cassettes and waiting agonizing minutes while bizarre sci-fi sounds blared out. But watching that little blocky 8-bit satellite orbit a digital planet sparked a lifelong obsession. It proved that a virtual universe inside a computer could feel incredibly real and, honestly, a lot more malleable than the unreachable reaches of actual space.
Which brings us to Chapter 1, the Cosmic Laboratory. Let's see how that childhood game evolved into the most advanced scientific laboratories on Earth.
You see, unlike a chemist mixing compounds or a biologist studying cells, a cosmologist can't just stick the universe into a test tube. You absolutely cannot isolate a galaxy, tweak a variable, and just wait 1 billion years to see what happens. That's the fundamental roadblock of cosmology. You cannot experiment on the universe. So what's the workaround? Virtual worlds. Cosmologists use incredibly powerful computer simulations as their laboratory. Inside these digital sandboxes, the immense bounds of space and time are finally under our control. You can hit fast forward on cosmic history, tweak the fundamental laws of nature, and watch exactly how the cosmos reacts.
Moving on to Chapter 2, From Ants to Galaxies. Simulating systems of this magnitude requires a massive conceptual leap. Think about army ants for a second. A single ant? Pretty simple. It follows very basic biological impulses. But when you swarm millions of them together, they perform extraordinary feats of architecture, like using their collective bodies to build living, breathing bridges over huge gaps. It's a perfect analogy, because just like you can't predict a complex ant bridge by studying one isolated insect, you can't anticipate the stunning, intricate cosmic web of galaxies just by looking at the isolated physics of one lone star. You have to look at the collective.
The key here is emergent complexity. There is no executive ant drawing up blueprints for the bridge, and there is certainly no grand organizer directing traffic out in the cosmos. The overwhelming sophistication we see in the night sky emerges purely from millions of components relentlessly following simple, unchanging rules. And computers are the absolute perfect tool for this, because they're incredibly fast and totally unyielding at basic arithmetic. They apply simple rules like gravity, radiation, and light to billions of digital elements millions of times a second. Let the simulation run, and a highly organized universe naturally emerges right out of a chaotic melee of primordial gas and dust.
Next up, Chapter 3, the limits of computing. Because crunching all that math brings us face to face with an absolute technological wall.
Let's quickly ground ourselves with the basics. A bit. We all know it's the fundamental 1 or 0 switch of computer memory, right? It's the absolute foundation of everything digital. That childhood ZX Spectrum had almost 400,000 bits. Your modern laptop has roughly 100 billion. And the world's largest supercomputers, they're rocking tens of thousands of trillions of bits. Sounds like an infinite playground, enough memory to simulate reality itself. Or is it?
Well, just think about trying to simulate the weather on our own tiny planet. Earth's atmosphere contains roughly 10 to the power of 44 molecules. If we wanted to store just a single bit of info to track every individual molecule for a basic afternoon weather forecast, we would need a 10 to the 21st power increase in the storage capacity of all the world's computing centers combined. Just let that number sink in for a second. 10 to the 21. It's not just practically hard to track every atom, it literally defies the physical limits of computing.
Because we don't have infinite computing power, scientists simply have to cheat. They use incredibly crafty physics shortcuts. Instead of calculating the trajectory of every single particle, they have to lump vast clouds of material together. They rely on the broad strokes of fluid dynamics instead of tracking individual atoms, basically describing how huge pockets of gas move in mass, transport heat, and collide. The true art of cosmological simulation lies entirely in these clever compromises. It's all about knowing exactly what details to blur out so your computer doesn't instantly crash under the crushing weight of reality.
This leads us to Chapter 4, The Modeler's Oath, because taking those mathematical shortcuts can sometimes have massive, real-world consequences.
Humanity's attempt to predict the unpredictable is full of hard lessons. Back in 1854, a member of Parliament was literally laughed out of the British House of Commons just for suggesting we might one day know the weather a day in advance. Fast forward to the early 2000s, and the pristine sheen of computer predictions made us dangerously overconfident. Huge financial hedge funds started hiring theoretical physicists, known as quants, to build complex simulations of stock market movements. They used simple assumptions to model incredibly volatile systems. And fund managers blindly trusted these simulated prophecies as absolute truth, totally ignoring the massive risks of rare market falls that their algorithms had elegantly smoothed over. The direct result of trusting the simulation over reality? The devastating 2008 global economic crash.
Following the wreckage of that crash, leading quants published what they called the Modeler's Hippocratic Oath. It's a powerful statement. I will remember that I didn't make the world and it doesn't satisfy my equations. I will not give the people who use my models false comfort about their accuracy. It's a stark, absolutely vital reminder to cosmologists that their virtual universes are fundamentally flawed. They are approximations, not reality. To truly gain knowledge from a simulation, you must maintain a deep, unwavering humility about its limitations.
Keeping those strict limitations in check, we arrive at Chapter 5, Simulating the Unseen. This is probably the most mind-bending challenge of all.
To make a digital galaxy behave like a real one, to get those beautiful swirling spiral arms of the Milky Way to form correctly on a screen, we actually have to inject fantastical ingredients directly into the code. I'm talking about dark matter and dark energy. These are utterly exotic substances. We've never touched them, never encountered them on Earth, and they remain completely invisible to even our most powerful space telescopes. Yet if programmers leave them out of the equation, the digital simulation literally tears itself to pieces. It forces us to accept that the physical rules governing the vast majority of the cosmos are radically, uncomfortably different from our everyday human experience.
The universe follows an unbroken chain of cause and effect stretching back 13.8 billion years. But what toppled the very first domino? Well, since the entire infant universe was once microscopic, simulations reveal it was completely ruled by the bizarre laws of quantum mechanics. At the subatomic level, particles don't sit still, they jitter and fluctuate randomly. In the tiny early cosmos, these random quantum jitters created incredibly lucky accidental differences, a fraction more matter here, a tiny bit less over there. Over billions of years of cosmic expansion and gravity, those tiny accidental seeds amplified and grew into every massive astronomical structure, every swirling galaxy, brilliant star, and rocky planet we see today.
So, these simulations reveal a pretty uncomfortable truth. Our universe could easily have looked entirely different. If a single microscopic particle had jittered slightly to the left instead of the right 13.8 billion years ago, the Milky Way might never have formed. I want to leave you with this provocative thought. Next time you look up at the night sky, ask yourself, is everything we know and everything we are just the incredibly lucky result of a random quantum jitter at the very dawn of time? It's a profound mystery and one we're going to keep chasing as we try to code the cosmos.